Hey, so we're going to start 5.3 solving quadratics by using square roots. The reason why we don't have PowerPoint right now is because I'm going to be doing this on the chalkboard. So the essential question is going to be, how can we solve quadratics using square roots? How can we solve quadratic equations using square roots? The square root symbol is also going to be called the radicand or radical symbol. And the number under that radical symbol is going to be known as the radicand. So in order to simplify radicals, if the radicand is not a perfect square, you write it in prime factors. Then pairs come out of the radical as a whole number. So we're going to see the following. I'm going to do this in two different ways. So I might show you a way that you have not learned before. Just be patient with me. 45 breaks up into 9 and 5. And if I stop there, because 9 is actually a perfect square root, I can break this square root of 45 into square root of 9 times 5. I can also separate those square roots into square root of 9 times the square root of 5, and the square root of 9 becomes 3. And the square root of 5 is not perfect, so I just leave it as 3 root 5, or 3 times the square root of 5. The second way is probably what you're more familiar with. So 45 breaks up into 9 and 5, and then 9 breaks up into 3 and 3. So if I wrote the prime factorization under the square root, we have 3 times 3 times 5. And wait, 3 times 3, sometimes teachers circle a pair and then they write it outside the radical as a whole number. I just wanted you to see why we do that. It's because 3 times 3 is a perfect square root, or a perfect square, and the square root of 9 is actually 3. So I'm going to do it again, just as a reminder. 72 can break up into 9 and 8, and 8 actually breaks up into 4 and 2. I'm looking at the perfect squares. So 72 can be rewritten as 9 times 4 times 2. And that can also be, that can also be rewritten as square root of 9 times the square root of 4 times the square root of 2. Square root of 9 is 3, square root of 4 is 2, and then square root of 2 cannot be broken down, and it's left as a square root of 2. Looking at this the second way, probably what you're more familiar with is completely factoring, finding all the primes, and circling the pairs, and recognizing, okay, I've got a pair of 3s, a pair of 2s, so they go out of the radical symbol, and I'm left with 1, 2, which doesn't have a pair, so it's going to be left inside the radical. I get the same answer. I'm probably going to be doing the circling of pairs and bringing them out, but just letting you realize it's because they come from perfect square roots. So there's something special where if the radicand is a fraction, both the numerator and the denominator can have the radical. They can get the radical symbol. So then there's something special called rationalize. We're going to need to rationalize the denominator. It's going to look like the following. After we put the square root of the quantity 3/4, we're going to put the square root of 3 divided by the square root of 4, and recognizing that the square root of 4 is a perfect square, becoming 2. When the denominator becomes an integer, we don't need to rationalize the denominator. However, in the next case, we get the square root of 7 divided by the square root of 5, and that is not an integer. We call this bad math grammar. So the way to correct it is we're going to multiply the numerator and denominator by the square root of 5 over the square root of 5. It's called multiplying by a form of 1. Whenever we take, so just listen for a little bit. If you took 2 divided by 2, you get a 1. 3 divided by 3, you get a 1. Negative 5 divided by negative 5, it's a 1. So square root of 5 divided by square root of 5 is like multiplying by a form of 1. You're not changing the previous value. So the purpose of this is to get the square root away from the denominator. Continuing on, square root of 7 times the square root of 5 becomes the square root of 35 over square root of 5 times the square root of 5 is the square root of 25. This is now a perfect square root. It's going to turn into 5. So the final answer would be square root of 35 divided by 5. So on to the next page. When you introduce a square root into an equation, or when you take the square root of both sides in an equation, you've got to put a plus or minus symbol in front of the square root because we need to recognize, okay, so what squared equals 9? Well, actually, 9 can come from two different possibilities, either positive 3 being squared or negative 3 being squared. So when you take the square root on both sides, we need to recognize that that's not only could we get a positive 3, we also could get a negative 3. So include the plus or minus, which is what we'll see on this back page. So solving these equations by square roots, we're going to get the x squared on one side by itself by adding 8 to both sides, and then taking the square root. When we take the square root, we're going to include the plus or minus symbol, and then we will rationalize. So 8 can be broken up into 4 and 2, and wait a second, I just said on the previous page that I'm going to use like the pairs or whatever, but right now, wait, square root of 4 becomes a perfect 2. So this square root of 4 becomes 2 times the square root of 2. So my answers are plus or minus square root of 2 root 2. So before I can do the square root method, I need to get everything to one side. Because I noticed that x squared, the smaller valued x squared, if I subtract x squared to this side, I'll get a positive 2x squared. So I'm going to get everything to the other side. That's what I'll be doing. So I want a 0 on this side. When I subtract 2x, or when I subtract x squared, I get 2x squared. When I add 8x, I get no x term. When I subtract 30, I get negative 48. All right, so now I'm just going to, wait, when I only have an x squared term, that is when I'm going to use the square root method. It's going to be quicker. Add 48 to the other side. Divide by 2. Take the square root of both sides and include the plus or minus in front of the square root. And rationalize. So 24 has a perfect square of 4, and then I'm left over with a 6, which is not a perfect square root. And it's only broken up into 2 and 3. So I'm going to recognize that it's going to be plus or minus, well, square root of 4 is 2, times the square root of 6. That's what x is. Number 7. So with number 7, let's get everything to one side. So subtract 3x. We get x squared plus 2x minus 24 equals 0. Wait a second. Hold on, I can't do the square root method like this because I don't have a perfect square. So here's a situation where I'm not just left with an x squared, I also have an x. I cannot use the square root method. I have to go to a different method. Since we learned factoring yesterday, let's do it. We've got to figure out what multiplies to negative 24, adds to 2, and we've got negative 4 and positive 6. What would make each of those the zero product? Or if we have a zero product, we're going to recognize, okay, what if this first set of parentheses was the 0? X would need to be 4. In the second set, if that parentheses needed to be the 0, the solution would have to be negative 6. So let's go over to 8. In problem 8, if I added 7, my bad, let's recap. I'm only having an x squared in this problem, so I can do the square root method. Add 7, divide by 2, and now let's take the square root on both sides, and when we do, we're going to include that plus or minus. So wait a second. We now have a fraction that if I had square root of 7 over the square root of 2, it's not going to be perfect. So I'm going to need some work. Let's separate this into square root of 7 over the square root of 2. We're going to have to multiply top and bottom by the square root of 2 over 2. My bad. Let me rephrase. We're going to have to multiply top and bottom by the square root of 2. It's multiplying by a form of 1 because this is bad math grammar. We can't have a square root in a denominator. So we've got plus or minus square root of 14 over the square root of 4, which becomes plus or minus square root of 14 over 2. Let's talk about reducing. Some of us may want to say, oh, 14 reduces into 2. The bad thing is this is the square root of 14. And square root of 14 is not a same term as a whole number. We've got an irrational number with a whole number. We can't simplify that. They have to be either both rational or they have to be both irrational numbers. So now let's find the zeros of the function. This is more of the application, just like yesterday. The word zeros means x-intercepts, which also means that it's going to be some sort of x-coordinate comma 0. There's got to be a 0 for the y-coordinate. We set that 0, or we plug the 0 in. And this is a case where I only have the x squared term, so let's keep it. Or, my bad. So let's solve it by doing square roots. Subtract 6. I guess I could have added x squared, so that way I didn't have to deal with a negative. But either way, divide by a negative 1, and then take the square root on both sides, include the plus or minus. So my answer is plus or minus root 6 equals x. Since 6 does not break down into any sort of perfect squares, I'm done. So homework over this lesson is the following. Page 267, numbers 52, 53, 58, 60, 61, 62.